All right, let's do some applications of angle measure problems. And let's start by looking at problems that involve using degrees, minutes, and seconds. So in our previous video, we talked about what a degree was, and it's a unit of measurement for an angle. Well, it turns out that we can be a little bit more specific than simply writing an angle in degrees. In the same way that we can measure time in something like hours, we can also have a smaller unit of time. Specifically, we can go from hours and break an hour up into 60 minutes, and then take a minute and break it up into 60 seconds, and we can go into milliseconds and so on. And the same kind of application or process applies when it comes to angles. So while we think of an angle as there being 360 angles in a full rotation or in one circle, you could actually get more specific. You could break up a minute into a smaller measurement. Specifically, that's known as a minute. So we take a degree and we break it up into a minute, or into 60 minutes, if you will. So I would say 1 degree would be equal to 60 minutes. And we can write out minutes, but to be a little bit more specific, or I should say more concise, we can use this symbol to indicate that it's a minute. So 1 degree is equal to 60 minutes. Well, that minute you can then break up into 60 seconds as well. So you're starting to see a pattern here. It is very much like, think of 1 degree as being 1 hour, if you will. Right? And I know that seems a little confusing because with an hour you think of one full rotation being 1 hour on the clock. But if you can think of a degree as an hour, then you can understand that there are 60 minutes in 1 degree. And then when in 1 minute, there are also 60 seconds. So then ask yourself, how many seconds would there be in 1 degree? And the answer is 3,600 seconds. Okay? So some word problems involve being more specific than just degrees. They will have you write an answer in terms of minutes or seconds. So it would be a good idea for us to know how to convert from degrees into minutes and minutes into seconds, and also how to go from degrees into just decimal form. So let's take a look at this first one here. Let's look at these few here. So first off, let's convert these into decimal form. So 45 degrees, 30 minutes. Well, let's write that as a decimal. So 45 minutes, nothing is going to change there. This is just still 45. Did I say 45 minutes? 45 degrees, that's still 45 degrees. That hasn't changed. Now what we want to do, and let me just change colors here. I want to change this 30 minutes into degrees, right? I want to write the 30 minutes into degrees. That's our goal here. So think about this for a second. Well, 30, we would say 30 minutes. And this is just basic unit conversion here. 30 minutes, we know that there is 60 minutes in 1 degree. So we can pretty much just kind of divide out those units here. 30 goes into 60 twice. So we have here, you can write this as 45 and 1/2 degree, or in decimal form, 45.5 degrees. And that makes sense if you think about this, that this would be 45.5 degrees, because 30 minutes is half of 1 degree, given that we know that there are 60 minutes in 1 degree. Okay, let's try one that has both degrees, minutes, and seconds. So let's try number 2 here. So this is something like number 2. We would leave the 212 degrees alone. That's going to be as it is. So I'll just write that 212 degrees. That's as it is. But now let's convert to 14 minutes. So using the same process that we did before, we would say, all right, let's take that 14 minutes and convert it into degrees. There are 60 minutes in 1 degree. And then let's also convert these seconds into degrees. Now, if you want, you could take the seconds and convert them into minutes, and then convert that back into degrees as well. But if you also could just say, hey, I know that there are 32 seconds in, I have 32 seconds, and I know that there are 3,600 seconds in 1 degree, and do the conversion that way. If you take these values and put them into your calculator right now, given that we're working in decimal form, that's fine. You could also be you could write this as an exact fraction as well, but let's just go with a decimal approximation. We've got approximately 212 plus, and this is about 0.23, and that 3 is going to be repeating. 32 divided by 3,600 is going to give us 0.008, and that's repeating. And these are all in degrees. What we've done is just converted the minutes and seconds into degrees. So altogether, this comes out to 212.2422, and this is going to keep on going, but we'll just write this as degrees. Okay? There's that value there. All right, now let's go from degrees, minutes, and seconds into, let's take an angle that is given to us in just degrees, and let's convert it into degrees, minutes, and seconds, or DMS for short. So this 25 is just going to be 25 degrees. That's easy. Now let's take that 0.7625, and I'll use a different color for this. Let's take that 0.7625 degrees, and let's convert it into degrees, or into minutes. Well, how many minutes is this? Well, this time we're going the other way. I know that in 1 degree, there are going to be 60 minutes. So if you do 0.7625 times 60, all of this should come out to 45.75 minutes. So what we can now write is we've got 25 degrees. We've got 45 minutes. Let me just change that. But what about this 0.75? This is 0.75 of a minute. We need to convert that into seconds. So 0.75, again, same kind of deal. We're going to have 1 minute has 60 seconds. So when we convert that, see here, let me just punch that into my calculator. So 0.75 times, oh, I didn't need a calculator for that. I was checking the previous one. That's going to be 45 seconds. There's also a way to do this in your graphing calculator, and it's hard for me to kind of explain this over this video. But if you go ahead and hit second on your graphing calculator, second, and then hit the apps button and option number 4. So let me actually write it out. Those of you who have a graphing calculator, you can, in your calculator, you can write the second button, then hit the apps button. Okay. And then if you go into option number 4, you'll see that there's DMS. So you can take an angle. You could just try it with the last one that we just did. Take this angle here in decimal and then hit DMS, and it should automatically convert it into degrees, minutes, and seconds, which is kind of a neat feature of most TI graphing calculators. All right. Now let's go ahead and let's talk about another application. Now that we're hopefully a little bit more comfortable converting into degrees, minutes, and seconds, let's talk about arc length. So let's suppose, let me actually go back and do this in black. Suppose we have a circle, okay? And in this circle here, we are able to draw a certain radius. So let me just go ahead and draw this. We're going to say this is our radius here. And let's go here, something like that, all right? We know that both of these, assuming that this is the center, both of these lengths here are going to be the radius. And then within that, we can also identify that this here is what we call our central angle. This is our central angle. It's an angle where the vertex of that angle is the center of the circle, hence the name central angle. And that central angle is always going to be in radians. Keep in mind, this is always in radians. We never write our central angle in degrees because, remember, as we discussed previously, a radian is a way of measuring an angle with respect to the total angle measure. So it's a ratio, if you will. Now, we would say that this central angle intercepts an arc length. And let me actually just kind of highlight this so we can see. This here is our arc length. We call this S. We often denote arc length as S. Well, what do we know about the arc length here? We know that this arc length here, which we'll describe as S, is a certain ratio of the entire circumference of the circle. So whatever the entire circumference of the circle is, we know that the arc length is a certain ratio or fraction of that. And that is going to be proportional to whatever our central angle is, all right, central angle, which we often denote as theta, with respect to the entire angle measure of the entire circle. Entire circle angle measure. And if we plug in what we know here, we can say the following. Our arc length, which is S, well, what is the circumference of the circle? We know the formula is 2 pi r. The central angle we're going to denote as being theta. And the entire circle's angle measure, one full rotation, is 2 pi. Well, if we then try to isolate s, if I try to get s by itself, we see s is equal to theta over 2 pi times 2 pi r. And if we simplify this, we divide out the 2's, we divide by the pi's, or divide the pi's out, what's left over? We would say the following. Let me actually just move this over here so we can simplify this. We could say the following. S is equal to theta times r, or r theta. And what do you know? We have just derived the formula that will give us the arc length of any arc on a circle, provided that we have the circle's radius and that central angle. And if that helps you remember this, just remember the phrase standing room only. And that's kind of a cheat because I'm kind of using theta and writing theta with an O, but if that helps, maybe just do this, being a little clever there. Just a way to remember it. Or you could just say, you know what, you don't need to give me a phrase. It's a really easy formula. S is equal to r theta. That works. All right, so now that we have that formula, we've derived it, let's use it. Let's find the measure of the central angle in a circle with a radius of 6 that intercepts an arc of 18 centimeters. So using the formula, S is equal to r theta, plug in what we know. Our arc length is 18. Our radius is 6. We're then going to solve for theta, because that's what we're trying to find, the measure of the central angle. Theta is equal to 3. 3 what? 3 radians. Okay? And you don't actually need to write radians. If you just write the number 3, it's implied there that your angle measure is in radians. Okay? Now, as soon as you do this, now we're getting into trouble, because now you're telling me it's in degrees, which it's not. Okay? So just to recap, we know that our arc length can be found by doing S is equal to r times theta. We're then going to use this arc length to calculate things like linear and angular speed. Okay? Really quickly, I guess there is another problem here where I'm asking you to find the arc length that's intercepted by the central angle. And notice this time I'm giving you the angle in 240 degrees. So what that means is I'm going to need to take this angle that's in degrees and convert it into radians. So I'm going to say there's 360 degrees in 2 pi radians. And then we're just going to multiply this by 4. Or we could have just done this pi over 180 if that's easier for you. And then we're going to multiply this all by a radius of 4. So this is our angle in radians now. This was our radius. And this should then just come out to S is equal to 4/3 or 4 pi over 3 times 4. And so you should get 16 pi over 3. Okay? All right. And let's see here. Okay. That works. All right. So now going back to talking about arc length and its relation to linear and angular speed, let's break each of these terms down first. What is linear speed? Linear speed refers to the speed that something, an object or particle, moves around a circle. Okay, so if we have a circle, and maybe you can think about this circle as like a tire, for example. So if we have a circle, and we're tracking the speed at which this particle is moving around the circle, that would give you our linear speed. Okay, so imagine you can even like take a tire, and if you were to prick it with a needle, or let's say it ran over a nail, and so now you've got this nail protruding out of this tire, and you would track the amount of distance that this nail has now covered as it goes around, as this tire rotates or turns, and you're really just keeping track of the amount of distance that that nail travels over time, that would be giving us linear speed. On the other hand, if you had something like angular speed, what we would be seeing is over a certain amount of time, and let me make that theta a little bit more clear, over a certain amount of time, how much angular space, if you will, has been covered. Okay, so what is the speed that the angle is changing within a circle? So how do we figure out both of these formulas? Well, let's start with linear speed for a second. What do we know about linear speed? I just said that it's the amount of distance that a particle has moved over a certain amount of time. We just said that we can calculate the distance, this arc length here, that's a terrible arc, but this arc length here, right? If I said arc length, how much has that changed over time? I can just say my linear speed is s over t. Okay? So we say s over t is our linear speed. Really easy. Just our arc length over time. That's all it is. Now what about our angular speed? Well, that would be how much the central angle has moved. The central angle over time as well, which it would be theta over t. Let me just kind of zoom out here so we have some space. So we say that our angular speed is theta over t. Now when we're doing problems that involve finding both linear and angular speed, I often recommend finding angular speed first. Well, why is that? Well, because I know that linear speed, if it's arc length over time, s is equal to r theta. We can also write this as our linear speed just simply being our radius times our angular speed. So if you're going to find your angular speed anyway, then you just need to multiply by whatever your radius is, and boom, now we've got our linear speed. Okay? All right, so let me do a couple practice problems here just to make sure that we get a sense of this. They get a little bit more difficult, but really if we keep these ideas in mind and are really just prioritizing our unit conversion, these shouldn't be too much of a problem. So a car has tires that have a radius of 16 inches. So let's just go ahead and just kind of draw that. Okay, a radius of 16 inches. Probably need to zoom in on this. If the tire revolves 7 times per second, find the linear speed of the tire. All right, so like I mentioned before, I'm going to start with the angular speed. I'm going to start with the angular speed first, which I know is theta over t. So if we are talking about a full revolution, a full tire revolution, well, what is that angle measure? In one revolution, I know that my central angle will be 2 pi. But if I rotated 7 times in a second, then I would say 7 times 2 pi over 1 second. So I would say 14 pi radians per second. That's my angular speed. To find my linear speed, I'm just going to take what I just found. So I would say my linear speed is equal to r times theta over t. So if our radius is 16, I'm just going to go 16 times 14 pi radians per second, which would be, actually, let's not do that here. Actually, I'll keep that there. I'll just make it a little bit smaller, which comes out to be 224 pi inches, and I should probably have noted that here, that my radius was in inches. Okay, so this is going to be in inches per second, because I've just now talked about the distance traveled over time. Okay, all right, what about a clock's hand now? So if we say a clock's hand is 9 centimeters long, s is equal to r theta is our arc length. Find the linear speed of the second hand. Well, let's figure out our angular speed. So in centimeters per second, let's think about this. Find the linear speed of the second hand. Well, if we're tracking how much time that the hand has traveled in 1 second, that would be 1 over 60 because there's 60 seconds, right? And in that time, we would say that our arc length in one rotation, let me just actually write the arc length here. This was a radius of 9, and our theta would be 2 pi. So in one full rotation, the arc length was 18 pi in one full rotation. So in one full rotation, I'm going to write that here, 18 pi over 1, which was 60 seconds. This is in 60 seconds, right? One full rotation. I'm seeing what was the linear speed, how much distance did I travel in that time? This would then have to be 3 pi over 10 centimeters per second. Okay? All right. I'm working on this during my prep just to give you a heads up. So the bell's going to probably ring in just a minute, but I'll finish up these problems or as much of it as I can. Let's do this record player problem. So we've got a record player, and it can play a 12-inch record at either 33 rotations per minute, or RPM, or 45 rotations per minute. And I know that most of you probably need a little bit of context because some of you haven't even seen a record player before. But the idea is that a record is kind of a flat disc that moves around at a certain speed, and there's a needle on it, and depending on how it hits the record, it plays music. That's besides the point. Just you need to know that it's a flat disc that's rotating around, okay? Now, if the A side, there's two sides to every record. If the A side of the record runs for 25 minutes, how much farther or further would a 45 RPM record have traveled in the total compared to that 33 RPM? Okay, so let's break this down. First off, let's look at a 45 RPM record. 45 RPM record. Okay, so how much distance did that travel? We're effectively finding our arc length. S is equal to R times theta. If our diameter was 12, that means our radius was equal to 6. So we're going to say our radius is 6. Okay, that's our radius. Now we need to find the central angle. Okay, now what was our angle? So this is our radius. What was the angle? Well, we know that in one rotation, the angle is 2 pi. But how many rotations were there in this 1 minute? There are 45 rotations. 45, the number of rotations in a minute. So what we're saying here is, over the course of an entire minute, 45 times 2, that's 90 pi. There's the bell. I'm going to wait that. That's 90 pi. So that's the amount of angle that has elapsed or that has changed or has moved over the course of 1 minute. So we would say that this would be 540 pi inches per minute. Okay? Now, we are comparing how much has traveled in over the span of 25 minutes. So I'm now going to take this amount. Let me make this a little bit smaller so I have some more space to work with. So now that I have 540 pi inches per minute, I'm now going to multiply this by 25 minutes to figure out how much now distance has been covered in that time. And that's going to be 540 times 25. That's 13,500 pi inches. Okay? So what we did, just to kind of recap our process here, we found the angular speed. We found the angular speed here. I'm actually get rid of the S because that might have been a little bit confusing. To find the linear speed, we found the angular speed, which was 540 pi radians per minute, and then we multiplied it by our radius, which was 6. What that then gave us was our linear speed here. Once we know our linear speed, we can calculate the amount of distance traveled over the course of 25 minutes. So go ahead and try that process again now. I'm going to do this in a different color. Go ahead and now do this for 33 rotations per minute. Pause the video and give that a go. So here, to find our linear speed, we're going to take our same radius, 6. We're going to multiply it by our angular speed, which was 2 pi times 33 rotations over the course of 1 minute. All of this comes out to be 396 pi inches per minute, because that was our linear speed. And then we're going to multiply our linear speed times the 25 rotations. And that turns out to be 9,900 pi inches. Okay? And that was how much was traveled over 33 rotations per minute. So I'm now going to go ahead and subtract these two. So 13, I would normally have a little bit more space. I apologize for the lack of space here. Minus 9,900 pi. Let me just zoom in on that. So we would say that record A, or the side that travels 45 RPM, travels 3,600 pi inches more over the course of 25 minutes than does the side that rotates at a speed of 33 RPM. Okay? All right. Let me do one more problem because I think this last one is actually a good one. Okay, so let me do this one problem. Unfortunately, now I have some space to work with. Assuming that the Earth is a sphere, okay, for all of you flat earthers out there, last time we all checked, meaning the smartest people in the world checked, it was not flat. It's actually a sphere. So assuming that the Earth is a sphere of radius 4,000, and I think that's more the assumption here we're making. So we have a sphere here, and the radius is 4,000. Okay, and 4,000. And the cities are on the same longitude. One is due north of the other. Find the distance between Johannesburg, South Africa, which the latitude is given, and Jerusalem, Israel, and that latitude is given. Okay, so there's a couple of probably conceptual and contextual things that we need to break down. So first off, if we say that the Earth is indeed a sphere, we can draw this as follows. I'm going to just kind of draw this just to indicate that we indeed have a sphere. So hopefully that helps kind of see the fact that this is three-dimensional. It's a sphere. Next, we've got two cities. One is due north of the other. So if this is, we're going to say Jerusalem. And the other one is, where was it? Johannesburg. Johannesburg. Okay, these cities are due north of one another. Okay, so if we were to kind of turn this globe so that you were facing it directly, but basically what we would be saying is that we have one city here and one city directly due north of the other, or one city is directly due south of the other. So they are vertically aligned, if you will, if that kind of helps make sense of that. But I'm just going to kind of draw them here because in the context of this question, it will actually make more sense to think of it that way. Right? So one city is due north of the other. What we're given are their latitudes. So it says that Johannesburg has a latitude of 26 degrees and 8 minutes. And what that effectively means here, is that Johannesburg is 26 degrees and 8 minutes south of the equator. Okay? So we could say that this angle here is 26 degrees and 8 minutes south of the equator. What about Jerusalem? Jerusalem, we're told, has a latitude of 31 degrees and 46 minutes north of the equator. So this angle here, I'll just write this here. This angle here is 36 or 31 degrees. What was it again? Sorry, I just forgot. 46 minutes. There we go, 46 minutes. Okay, so both of these latitudes are with respect to the equator. So hopefully you can kind of conceptualize this a little bit better now. What we want to do then is effectively find the distance. Find this distance here between these two cities. So find this distance. Well, if we just isolate what we just were able to kind of highlight in color here, we're solving for x. And we have the radius. We're told that this radius is 4,000, right? Because again, it doesn't matter where that radius is going. Because this is a sphere, we know that this distance here is 4,000. This distance here is 4,000. So if we're given the radius, all we need to do then to figure out s, since s is equal to r times theta, we just need to know what our central angle is. And guess what? We have this angle here, and we have this angle here. So let's actually add those up. 31 degrees, 46 minutes, plus 26 degrees and 8 minutes. Okay? That's going to give us 57 degrees and 54 minutes. Okay? And now that I have that, I can set this. I can say my radius is 4,000. My angle is 57 degrees and 54 minutes. And you may want to convert that into, we're definitely going to have to convert that into radians, but you'll want to probably convert that into decimal mode first. So now this is our in radians. And if you go ahead and convert that, you should get 4,000. And this should come out to 1.0105 radians. And this turns out to be approximately 4,042 miles. Okay? So at first glance, that problem looked really complicated, but it really wasn't that bad. All we were doing is finding arc length. And the biggest thing here was really just the context, understanding how longitude and latitude works. And hopefully if you had a great world history or geography course, that wasn't too bad. But that's how we would set that up. Okay, so hopefully this video has helped understand a couple things about arc length and understanding as well some different types of applications of angle measure problems.